Thank you for this introduction, Wilge. Yes, constraint programming scheduling applications. In operations research, scheduling plays a major role, and constraint programming allows you to create schedules with various types of constraints. So let's get into it with a rather trivial example. First, I'll introduce, in this webinar, I'll first introduce you to our language for constraint programming, and during that presentation I'll also give two small demos, maintenance schedule and bridge building. So let's take a trivial example, how to handle a dinner. First, of course, that is the concept of dinner. After an appointment is made, you start prepping your dinner, cooking, you enjoy it, and of course you clean up. Nothing very difficult. But let's look at cleanup in some more detail. It's of course in a sequence. You collect the dishes, you rinse them, you wash them, and you place them in the cupboard. Again, nothing difficult because they're all ordered. But with wash, you get a choice. You either do it manually or you do the washing. So in the activities you plan, you have to to cater for the alternatives, do it manually or do it by the washer. We can also look at the preparation in more details, and then we come across another type of constraints which may be difficult to formulate sometimes, namely that the persons that are to enjoy the dinner would like to have them served at the same time, so we want to have the same end time type of constraint. This is all possible, and there are in industry the number of activities can go in the hundreds or sometimes even into the thousands, and you want to have a proper schedule that either minimizes the make span, the total time to do all the activities, or to avoid tardiness, delivering too late, things like that. So there are many types of different constraints in scheduling programming. And in order to have a solution in a reasonable amount of time, AIMS is linked to CP optimizer technology. They have various modeling constructs for creating schedules, things I've just shown, but many more. And they have spent, by renowned scientists, many years on algorithm development to get a solution in reasonable time for scheduling applications. So how does this look in AIMS? The first thing, if you want to build a scheduling application, you want to think about the timeline. Am I thinking in days? Am I thinking in quarters? Do I just want to make an abstract schedule? If I just want to make an abstract schedule, I want to use a subset of the integers, period 1 to so many. If I want to have a link to concrete time, I can use the AIMS calendar construct. And once I have chosen that, I can formalize it in an AIMS mathematical program by filling in the schedule domain attribute. The second thing you want to do is which activities I want to actually perform. So in AIMS you do that by declaring them, and for each type of activity there is an index domain, and you can place a condition on the indices of that index domain in order to limit their number. Very important to activities is whether they're optional or not. Mandatory activities are of course scheduled, and that's the default in AIMS, but you can select the property optional, and with optional the activity becomes optional. It does not need to be performed. If we consider the dishwashing activity, you can do it either manually or with a dishwasher, so you model actually two activities, doing it manual and doing it by dishwasher. You give both of them the property optional, and you make sure via constraint that at least one of them is chosen. So that's why the property optional is very important also in the description of which activities are there. Once you have determined which activities are there, you also want to know more about these activities. Like the mathematical program, an activity has a scheduled domain attribute. In that you can denote the same timeline, or you can specify a subset of that timeline. The most elegant way is the B version, start time window and end time window, in which the activity must be present. So that's the way the activity can be modeled. Another very important part of an activity is its length. So how long does it take to execute that activity? There is a related attribute called size, referring to the amount of work, but I'll come back to the difference between length and size later on. The length attribute is, if you fill it in, you can get a defining constraint, like similarly, like with a variable at the definition attribute of a variable in aims. If you specify content therein, it becomes a defining constraint in aims. And it has the same restrictions, so you can specify a fixed length, or you can specify some expression that may depend on other variables. So that's declaring activities. But you can't. But you also want to constrain them, and the suffices of an activity provide you with a means to create simple constraints. There are five. The suffices correspond to 5 integer variables. There's an integer variable for the beginning, the end, the length, the size, and present. Length and size are similar. I'll come back to the difference later on. So each variable, each of these suffices is an integer variable, and you can provide simple constraints. For instance, if we look at our trivial example, the end of preparation needs to be before we can start enjoying the dinner, although some people enjoy cooking. The end of preparation, if we want to enjoy the dinner together, well, the dinner should be prepared for each person more or less at the same time. So that's also a type of constraint we can formulate easily with using these suffices. We say that an activity is active from its beginning, but not up to, but not including the end of the activity. Mathematical notation, we start at the beginning, but we do not include the end. That's important because with that restriction, we can simply say that the end is equal to the beginning plus the length, if it is present. Otherwise, the constraint programming solver does not enforce that constraint. Of course, if you do not select the property optional, present is always 1, so the if-then part can be ignored. But you also already saw that the constraints are only enforced if they are if the activities in there are only to be enforced if the activities are present, and that's why we have special precedence constraints in our language. Although I just denoted it using less than or equal, actually the preferred way of relating activities is via this type of constraint, end before the beginning. So we want to have the end of preparation before the beginning of enjoying the dinner, which is of course equivalent to if both activities are present, then the end is before the beginning. Why do we prefer this type of precedence constraints over the algebraic ones? Well, it's much more effective when doing the filtering of solutions which cannot be reached by the constraint programming solver that is underlying the scheduling engine of CPU optimizer. So we want to, in order to use the most effective and therefore reduce solution time, we want to use precedence constraints instead of algebraic constraints. There are 8 forms. The first part of the precedence constraint is the first activity, which we can refer either to the beginning or the end. The second part of the constraint name is whether it's at or before, corresponding to the equal sign or the less than or equal sign. And of course, the last part is again choosing between the begin or end suffix. The D argument, the third argument, is the distance. So we can say, well, let's wait 1 or 2 periods before, or we can wait some periods between those activities, which can be done by D. And the above precedence constraints, as I stated before, are only enforced if both activities are present. So if one of them is not present, they will not be enforced. We can also relate activities in various ways. If one activity consists of several sub-activities, perhaps ordered, perhaps not ordered, we can use it by a spanning constraint. So, by a spanning constraint. We can have also alternative ways to realize an activity, which we saw with the dishwasher, or doing it manually. And sometimes it's important to synchronize activities whereby some activities are taking place at the same time. But of course, these constraints only enforce if the involved activities are present. If some of the AI are present, it is enforced with these 3 types of grouping constraints. Now I come to the more interesting part, and that is sequential resources. Resources are sequential if they are, that's a general way of, with the resource type of identifier, we have a general way of constraining activities involved. Sequential resources are the type of resource that handle only one activity at a time. With a resource, you have to mention which activities are to be scheduled. So we have A job, B job with a grouping, and perhaps with a grouping with an additional condition on the index domain. We also suppose we have different type of resources of the same, multiple resources of the same time. You can of course generate them with an index domain. Then the a sequential resource will create a sequence of the jobs involved. So each job, there's only one job active at a time, as I said before. But there's also another powerful construct in that you can specify transition times, also known as setup times, or for example, if you have a painting machine, then between the painting of 2 cars, you need to clean the painting machine, and if you go from dark color to a lighter color, it takes more time than reverse, so the transition is more. Other types of transition are of course changing your location where you're working, things like that. So the transition is for the sequential resource a very useful thing. In order to specify, in order to further constrain the order of the activities, You can specify first, a last, the relations between activities, which one comes before the other, and whether a job becomes directly before another. You may also specify conditions on those relations. So I would like to switch now briefly to a demo. So let me first give the demo, and then let me explain how I declared, how I made the declarations. So I have a sequence of jobs. The first job takes relatively long, and the last job takes relatively small. I also have a time window, so job 1 can be starting at the first day up till the end of the calendar, but there is for job 10, as it is a relatively small job, it has a small time window in which it can be scheduled. So that corresponds to our intuition that big jobs will get also a big time window in which they can be scheduled. The small jobs get a small time window in which they can be scheduled, but they may be important for the same worker. So in order to sequence these jobs non-overlappingly, I can solve the problem. This problem, even though I would have difficulty doing it by hand, is very easy, of course, for a constraint programming solver. As you can see, the order of the jobs has changed. So the last jobs to be done is job 02, and the second job is job 03. And as you can see, the shortest job is still done in the middle. In blue, the actual jobs are done, and in yellow, the time needed to change from one job to the next. As you can see, there is one job with a longer change time that because it's a relatively short job to a relatively long job that might take more preparation. Don't know why, just a play example. So how did I model this type of problem? I just start with the first declaration. As you can see, I simply use the aims construct of day, of a calendar, and of a schedule mathematical program. I filled in the timeline. It is not really necessary. Aims will deduce the timeline if you do not specify it, but it's good habit to specify it anyway, in order to avoid mistakes later on. Of course, I have a set of jobs, and I can order them. The start and end time are relatively non-interesting. So what I've here done is that I've said that every job is to be started at a particular point and ended before another point in time, and that's my time window for that activity. It may depend on the index that I used here, and I have defining constraints stating that the actual length is to be what I've computed here in ACLAN, whatever that may be. Then I have a sequential resource. Again, I use the timeline, all meaning that it can be used during the entire timeline we defined. All my activities are to be scheduled on that sequential resource. And here with the transition, I can state, well, how long it takes to do a transition from one job to the next. And that's a rather easy way of specifying setup times compared to other forms of notation, I may say. Okay, this concludes my demo of narrowing, and I continue with my PowerPoint presentation. Sorry about this. Hope you liked the quick review. I continue now with parallel resources and declaring them. With parallel resources, also known in the literature as cumulative resources, you can do two things. You can do some kind of administration and see how much you have at the end, like when you record the money you earned or spent, or you can limit the number of resources you are using, resources of the same type typically. So parallel resources are resources that can handle multiple activities at a time. Again, you will need to specify the schedule domain. That can be the timeline you declared in the mathematical program or a subset thereof. And again, you'll need to specify which activities are to take place on that parallel resource. If you have multiple of the same type, then again, you can have an index domain. More interesting are the attributes that are particular to a parallel resource. You can specify the limit in the level range. You can specify an initial level, and you can specify how changes are to be recorded for activities. So the most typical one is a level change, but you can also say begin or end change. In the next slide, I'll show the difference between these three ways of handling changes. With a level change, or also known as a pulse, you specify the amount during which the activity level of the parallel resource is to be increased during the period that the activity is active, or rather between the beginning and end of that activity. With a begin change, you only increase at the beginning of the activity. During an end change, you similarly you increase the activity level of the parallel resource during an end change, and of course the total activity level needs to be within the range you specified in the declaration of that parallel resource. Now I can explain more the difference between the length and the size attribute, because I have the ingredients ready now. When modeling workers like human workers or machines that need maintenance regularly, they are not always active, and you can indicate that by using subsets of the timeline. So then the work done, if you have a human that takes leave during the weekend, then the work done between and if the human starts working on some project on Friday and finishes that on Tuesday, the length of that activity is 4 days, but the amount of work done is 2 days. So how do you so how can we specify and handle this? That is why length and size are slightly different. We say that an activity A is active during some time slot if it is in the schedule domain of that activity, and if it's in the schedule domain of every resource on which it is scheduled. So, and then we can define the size of an activity, and that is the number of active time slots that is in the range beginning up to but not including the end. And thus a size becomes a good measurement of the amount of work done by that activity. And we have, of course, an implicit constraint that if A is present, then the size is less than or equal to the length. Okay, now I'd like to do another demo. That's very good. Suppose I want to build a bridge, and in order to do that I need to have several pillars, and they have to be placed in a concrete block, and perhaps I need to drive some foundation below those pillars in order to get it stable. And once I have the pillars erected, I can place barriers on that bridge in order to allow traffic over that bridge. So how can we formulate that as a scheduling problem? Let me first let me go through the constraint programming model first, and then show how I can use that in a Gantt chart of aims. Each activity that is to be done is has some duration, and as you can see, it depends on the pillar and the type of work to be done. So I have two indices here. With these indices, I can enforce a ordering. So I want to drive in the foundation before I can do the concrete work, and then actually placing the pillar on top of it. If I want a bearer on a pillar, I have to place them on two pillars actually. So I want both a left pillar and a right pillar, which is implicitly in the way I've constructed it by use. So this type of constraint is typically used for various things. I can also simply use the greater than or equal if I want to. So that's I have various types of constraints. We using the modeling constructs CP Optimizer and aims are offering you. Then perhaps more interesting, I have a parallel resource, so I can use one or multiple cranes. I can use one or multiple pile drivers for the foundation, things like that. So for each type of machine I have a number available, and I model the level change of that activity by stating that if an activity is active and it's to be performed on machine M, then it will take that duration, and will take so much in change of this resource. And so now I can go to the demo part. Allow me to first solve it for using one machine at a time. So now you can see that it takes 150 days to build a bridge with 8 pillars. according to my modeling at least. And suppose now I want to say, well, if I want to have 2 times the number of machines, will that halve my time? Well, actually not, but so let's resolve it. And as you can see, it takes 92 days, and you can see how each of the machines is now being used. As you can see here, foundation piles can be can be scheduled at the same time, but this one can only start after the first one is finished, as we can see in the Gantt chart of aims. I would like to mention that the next webinar will be around solving NLP problems using parallel multistart, and it will be given on October 21, 2015.